Hello and welcome again to my channel. So today we'll be discussing a problem on differential equation. So and this is also a very important topic in NET, and we will be discussing today how many solutions of a differential equations are there. So we will be discussing uniqueness and existence theorem and see that the given differential equation has infinitely many solution or one solution or zero solution. Okay. And for the previous problems and more problems, we recommend to follow the following link. The link is also given in the description of this video. Okay. So the problem is find the number of solutions for the given ordinary differential equation 2 by 3 y prime is equals to y to the 1 by 3, and the initial condition is given as y0 equals to 0. Okay, so we have to find out what is the number of solutions of this differential equation. So first of all, we have to see whether the solution exists or not, and if exists, whether it's unique or not. And for that, there is a very famous theorem which says existence and uniqueness theorem. Okay, and for the hint, like you note that 0 is a solution of this differential equation. Okay, so now I recommend to pause the video and think of a solution, like how many solutions of this ODE is there, and then uh, watch the solution. Okay, so I hope you have tried this problem on your own. So, as I told, let's recall the existence and uniqueness theorem for the differential equation. So, let y prime is equals to f of xy with the initial condition that at the x0 the value is y0. Okay. Now let f of xy be continuous in some rectangle. So suppose that you have this is my x0 and this is my y0. So in some rectangle, open rectangle, that means yes, this is my R rectangle. So let f be continuous in some rectangle. So there exists some a and b such that x minus x0 is less than a and y minus y0 is less than b. Okay, and also bounded in this region. So I want the function to be continuous and bounded in some open rectangle. Then we say the solution of the ODE exists. Okay, so this says that if the function is bounded and continuous in some in some open rectangle, then the solution will exist. And moreover, if the partial derivative with respect to y is also continuous on R, then the solution is unique. So the partial derivative is continuous, then the solution is unique. Okay, so let's see for this function. So we have this differential equation 2 by 3 y prime. So this is my f. Okay, and x0 is 0 and y0 is 0. Okay, so this is, and this function is clearly continuous everywhere. So in particular, it is continuous in this rectangle. And of course, this is bounded in this rectangle. So we can take, let's say, for example, we can take a to be half, and b also to be half. So then this is clearly a bounded function in this domain, and hence the solution exists. Okay, but the problem is this uh, f of y equals to y to the 1 by 3. The partial derivative is not bounded on any interval containing 0. So, for example, what is the derivative of this? The derivative is y to the 1 by 3 minus 1, 1 by 3. So, this is 1 by 3, y to the minus 2 by 3. And at 0, this goes to infinity. And hence the partial derivative is not bounded. So yeah, so there is one like this thing is it is continuous as well as bounded is also needed. Okay, yeah. So this is not bounded and hence the solution need not be unique. I'm not saying the solution is not unique. The solution need not be unique. So see, if it would have been bounded, we can directly say that the solution is unique. Okay. So now let's see what are the solutions. So okay. So we can directly find because the problem is 2 by 3 y prime equals to y to the 1 by 3. So we can directly use the separation method to find out a solution. So 2 by 3 dy by dx is y to the 1 by 3, which I can write 2 by 3 dy by y to the 1 by 3 equals to dx. Now what is this? I just integrate this to get this. Okay. And now the integration you have y to the n integration is y to the n plus 1 by n plus 1 and is not minus 1. So we'll apply that y to the minus 1 by 3 plus 1 by 1 minus 1 by 3 plus 1, and this gives you y to the 2 by 3 because this is your 2 by 3 and hence this will be get cancelled, and y to the 2 by 3 is x plus c, and hence yx equals to x plus c to the power 3 by 2. And you use the initial condition that y0 is 0 to get y x equals to x to the 3 by 2, and this is a solution. Okay, and as I already told you that 0 is a solution because yx equals to 0, then if I take the derivative it remains 0, so 0 equals to 0 and it satisfies the initial condition, and hence this is also a solution. Okay, so you see that what I have is like 0 is a solution, so 0 is a solution, and y equals to 1 by 3 is also a solution. So it's like y equals to 1 by 3. So let's say it's like something like this. Okay. Okay. So this is your solution and this is also a solution. Then so then what it says that we will get all this as a solution. So this all are the solutions. So what we'll do, we'll just translate this line to get a solution. So in particular, if a is greater than 0, so this is my this is my a, this is my a, this is my a, this is my a. Okay. So after this, like I'm saying, all these are solutions. So if a is any real number and yx, if I define as 0, if x is less than equals to a, and yx equals to x minus a to the power 3 by 2 if x is greater than a. Okay, so this is the same thing, and then one can check that what is the, see what is y prime x? Y prime x is 0, 3 by 2 times x minus a to the power 1 by 2, because 3 by 2 minus 1, so it's 1 by 2. Okay, so what is this? This I can write 2 by 3 y prime x equals to 0 and x minus a to the power 1 by 2. Now, what is y to the power 1 by 3? See, if I take y to the power 1 by 3, this is 0 and this is 1 by 2. So this is equal to y to the 1 by 3. And hence it satisfies the differential equation, and therefore this is a solution. So for each a, I am getting a solution. So for each a, yax is a solution. And therefore this has uncountably many solutions, infinitely many solutions. Okay, so sometimes the option like ask like it has options in net, sometimes ask it has countable solution, uncountable solution, finite solution, or zero solution. So here, of course, it has infinite solution, but it has uncountable solutions. Okay, and hence the solution of this problem is completed. Okay, so thank you for your time. Again, tomorrow we will be discussing a miscellaneous problem. Uh, So tomorrow we'll be discussing a problem in the coordinate geometry, which is which was asked in the NBHM exam, and this problem was asked in CSIR exam. Okay, so thank you.